everyone, welcome to another video with I Learn Engineering. My name's Leslie. Today we're going to look at set theory, and set theory is it's a fundamental notion in discrete mathematics. So we have something called discrete mathematics, and it's a fundamental notion in that we're going to only cover the part of it that we need for computer science. There's a lot more to it, and if you're interested, you can dive down a really big rabbit hole. But for us, we only care about certain parts of it, so we're going to just look at that. So a set is basically a collection of objects, and the objects are called elements. So there's elements in that set. Excuse me. And we can have a set about anything we like. And normally we would draw a circle. And then we put our elements in that. And because my writing is really bad, I'm just gonna type mine in. So say I wanna have a set that is showing my cats, for example. I would draw my circle, and then I would put my cats' names in that circle. So that's my first set. That's a set of my cats. It could be numbers. It could be things that we represent, like colors, names of cats, anything that we want basically. We can also write it in a kind of formal way with curly brackets. So say I called my set C for cats, so it would be equal to, and then we always have our first curly brackets, and we type in the elements just like this, and then we close our brackets, and this is how we would denote our sets in a kind of formal way. So we call that a list notation because it's like a list of the elements in our set. So we can do either. We can have that circle with the elements in it, or we can see that list. So both are valid, both are correct. It really depends what we're doing. And if you kind of dive down that rabbit hole of everything else that's done, you'll see both. So then we have sets that are finite, and we have sets that are infinite, okay? So my set of cats is finite. I only have 3. I know how many I have. They're all listed there. It's a finite set. An infinite set could be, for example, all the positive integers from 1 all the way up to infinity. We don't know how many there are in that, because it goes to infinity. So how we would write that is we would start off with the same kind of thing. So say A equals, we open our curly braces, we put in the first so many elements, whatever we want, and then we have a ... like this, and then close. And the ... is what denotes that it is infinite. So if we think about this set here, that could be a set of all of those integers. We know that they're start at 1. We know they're positive numbers, and we know that it's infinite just from looking at that. So that would be our infinite kind of set. And again, that could be about anything that we want. It doesn't have to be integers. It could be anything. But it's a good example, I think. So we can also have repeating elements in our set. So let's imagine that I got another cat, and I give it the same name as one of my existing cats, because why not, right? If I had, where's my text? If I had another cat and I also called him Albert, and I had my set that looks like that, there's 2 repeating elements in there. Albert's repeated. Now, we don't actually write the second or third or fourth or whatever instance of that. We just write it once. So even though I have this set that has the 3 names in it, I could have more than one instance of each one of those. So they can repeat quite a lot, as many times as we needed to be, and that would be the same as well whenever we're kind of writing our list like this. We don't write every single repeating element, we just write it once. So hopefully that makes a bit of sense. I know sometimes the set theory can be confusing if you've never seen it before. I'll move this up a tiny bit. It's also worth noting as well that there's no order in a set. So say I had this set. I'm just going to put a couple of things in it. So say this is my set. So this set A is also the same as this set A. And it's also the same as this set A. So all three of those are basically denoting the same set. There's no order. We can write them whatever way we want. They all mean the same thing, basically, in terms of set theory. So what list you've written your set in doesn't mean that it's set in that order. It can be written in any order that you want. Let me move that up a little bit again. So we have three kind of common sets. We have the natural numbers, we have integers, and we have what was the other one? Rational numbers. I had my mind gone blank there for a second. So these are some of the common ones that we can have: the natural numbers, the integers, and the rational numbers. So if we think about a natural number set, there's two ways that it can be done. Some mathematicians will do it one way and some will do it the other way. I have seen it more so on the computer science side because that's my expertise. I've seen it more where we start with the 1. In terms of how it's preferred in discrete mathematics, it's not my area of expertise, to be honest, and I think there's a bit of controversy about it in there. So I'll show you both, but if we were ever doing it in computer science, we normally would start with the 1. Okay. So say I have a set A, and this is going to be my set of natural numbers. Okay. So you can either start it with the 0 like this. So some mathematicians will write them like this, and that they're infinite, obviously, natural numbers going for infinity. So that's one way of doing it. And then some mathematicians will start with the 1 like this, and obviously it's still infinite. So either one of those is correct, but some mathematicians prefer to do it one way or the other. So this would be our natural numbers there. Our integers then. Integers are whole numbers. They can be positive or negative. So we could write it like, I'll just put I for integer, that would be good. So we can write it like this. Oh, I need the dot first of all because it's infinite both ways. I always forget that. -1, 0, 1, 2, ... So we would write the integers like this because they're positive and negative. They're positive and negative whole numbers, and they go all the way from minus infinity right through to positive infinity. And then we've also got the rational numbers. So they are anything that you can write as a fraction. So I'll need to actually use my drawing skills for this one. So we'll call it R. And it, it's also infinite. So we'll put a wee dot. We'll put a wee dot. Put a wee dot. So it could be 1/1. It could be 1/2. 1/3, and so on and so forth. Put a wee dots in, and they're they're infinite. And again, they can be positive or negative as well. So that's the rational numbers. So they're the three that kind of common sets that you'll see all the time. Let me move this up a little bit. So as well as that, as well as having we've looked at the set notation where we have the circle. We've looked at the list notation with the brackets. We've looked at finite and infinite sets and what they mean and how to write them. We've looked at those common sets. So we've looked at the integers, the natural numbers, and the excuse me, and the rational numbers. We also have to think about elements and cardinality of a set. So if we think back to, and I'm going to write it down again, so I'll call my set C for cat. So I'm just refreshing our memory here. So that's my set of cats. So if I'm thinking about the elements within that, the elements within it would be Quakers, Albert, and Callie. So I could say that Quakers is an element of C. Or I could say that Birdie is not an element of C. So we can denote items as being in the list, as in they are an element in that set, or they are not. They're not in the set. So that's what we kind of think about as the elements of the items within the set. And then the other thing we want to think about is the cardinality of the set. The cardinality of the set is basically the size of the set, okay? And this only applies for finite sets because we can't know the size of an infinite set. It's not possible, it's infinite. So we want to say that the cardinality of the finite set is the number of elements in it. So the cardinality of my set C would be 3, because I've three cats. If I had 4, the cardinality would be 4. If I had 20, the cardinality would be 20, and so on and so forth. So the cardinality of the set is basically the size of the set. So you might see people, as you go through computer science and studying it, and maybe, in other, if you studied mathematics or something like that as well, you'll see people talk about the cardinality of a set, and it's basically the size. It's the number of elements that are in that set. And obviously only the finite sets. We also have something called an empty set, and it is, I'll have to use my pen again, so it has it's drawn like this. So that's the symbol that denotes empty, and then we just have the empty curly brackets. There's nothing in it. So the empty set is one that has a cardinality of 0. There's nothing in it. It doesn't have any elements, anything like that. Now we can have the empty set as a subset of another set, and it would count as one element even though it's empty itself. And I will give you a drawn out of what a subset looks like. So we'll take it back to my cats, because I'm obsessed with cats. I apologize for that. So this is my big set of all my cats, and we'll just put the names in there again. So we have Quakers, we have Albert, and we have Callie. Okay, so they're my 3 cats. They're in that set. But say I wanted to have a subset of cats that are out of the same litter. So I would have another set inside of that set, and then I would just put the names of those cats in there like this. So we can have subsets of our sets, and we can have as many subsets as we want. It's like, it can be like setception. I feel like we can have as many sets inside of our sets. So that's a simple example. I'm not gonna go too deep, because we don't necessarily need to go too deep in computer science, but we can have them as complex as we want. So a subset is a set that's inside the bigger set. It will contain some of the same elements. The bigger set, the whole set, should contain the most elements. It should contain everything. And then inside of that, we would have our smaller sets. So let's say we wanted to have a set of all the numbers from 1 to 5. So we'll have 1, we'll have 2, we'll have 3, we'll have 4, we'll have 5. And then maybe we want a subset of the, just the numbers from 1 to 2. So they're over here. And then say maybe we want a subset of the numbers from 4 to 5. So we have those over here, 4 and 5. Maybe we want a subset of all the numbers equal to 3. You can get as complicated as you like, and obviously it can be numbers, or it could be actual things like cats or pirates or whatever it is you want to have a set about. And we can have as many subsets as we like. We can have a subset within a subset, so we can go quite deep if we want to. But the big set, the outlying set, should have all of the elements that are in the subsets within it. So this is our foundation of set theory. As I said earlier, in discrete mathematics, there's a lot more about subsets and sets and set theory that those guys would be interested in. So these are the foundations that we need to know for computer science. We do also need to know about the relationship between sets, but that's quite a big topic, so we're going to have a separate video for that. So make sure you stay tuned for that one. Hopefully you've enjoyed this video of the foundation of set theory, and you've learned something from it. Thanks very much for watching. I'll see you again in another video. Bye.